This is section 3.3, increasing and decreasing functions and the first derivative. In this chapter, we're learning how the derivatives affect the graph of a function. And so, consequently, our stress is going to be on being able to graph a function using the information we're gathering from the first and eventually second derivatives. And consequently, graphing using the calculator sort of negates the need for that. So please want to stress that in this section, in this chapter, our goal is to be able to graph without a graphing calculator. So consequently, the test over chapter 3 is intended to be one where you will not be allowed the use of a graphing calculator during the test. And so make sure you have like a scientific calculator you can use for the test, because I'll let you use that for arithmetic. But just keep thinking all the time, I have to be able to do this without a graphing calculator, at least for the most part. There'll be a couple of things where we pull in a graphing calculator issue, I'm sure, but for the most part, that's kind of the thought process behind what we're doing. So we're going to learn how derivatives can be used to classify relative extrema as either relative minima or relative maxima. So we found out that in the last section that if you have a critical number, that is where the first derivative equals 0 or where the first derivative does not exist, that it's a critical number and then it is potentially a relative max or relative min, but not necessarily one of those. So we're going to learn today how to make that declaration, and again, without a graphing calculator in our hand, we're going to be able to say that. So first of all, let's talk about what it means for a function to be increasing. Kind of a simple idea. If you have an increasing function, then what that means is that if you were to pick any number in the interval that you're talking about, at least, and let's call that x sub 1, and then another number as an x value, let's call that x sub 2. And let's make it such that x sub 1 is smaller than x sub 2. It's a random decision, but that's the one I want to make. And if you are looking at the y values, if it's an increasing function, how does the y value at x sub 1 have to compare to the y value at x sub 2 if it's an increasing function? Well, obviously, the implication is that if x sub 1 is indeed smaller than x sub 2 and f is increasing, then f of x sub 1, wrote 2, f of x sub 1 will always give you, no matter what two x's you pick, such that x sub 1 is smaller than x sub 2, the y value for x sub 1 will always be smaller than the y value for x sub 2. Okay? And by the same token, if we have a decreasing function, like that one, there's x sub 2 and there's x sub 1. So this is the y value f of x sub 1, and this is the y value f of x sub 2. And again, if x sub 1 is smaller than x sub 2 and f is decreasing, and I'm not sure my handwriting on the above was very good. That's increasing. INC is the abbreviation I'm going to use for increasing. And for decreasing, I'm going to abbreviate that DEC. Then the idea would be that f of x sub 1, in that case, would give you a larger than f of x sub 2 value. And again, this is for any x sub 1, x sub 2 you want to pick for a decreasing function. As long as x sub 1 is the smaller of the two, then f of x sub 1 will be the larger of the two y values. Okay, so whenever we talk about increasing, decreasing, then you might realize that we're talking about movement from left to right. What's going on with the y values as x gets bigger and bigger? So as x increases, is y increasing for an increasing function, or is the y value decreasing for a decreasing function? The only other possibility besides these two is if it's not increasing or decreasing, then f can be constant, which isn't going to happen a lot of times. It will happen some. But if a function is constant on an interval, then f of x sub 1 would be equal to f of x sub 2 for any two x values you pick on that interval. And so let's talk about what that means as far as derivatives are concerned. So I don't have a constant function drawn there, so I'll do that in a second. Well, I'll do that now, I guess. Nope, I don't want to cloud things too much, so let's just leave that alone for right now. So if you pick any point on an increasing function and find the derivative, the first derivative, that'll give you the slope of the tangent line. And if it's increasing, what kind of number is f prime at, say, c, where c is just some number on the interval where the function is increasing? Well, if it's an increasing function, the first derivative will be a positive number because you have positive tangent line slopes. And when the function's decreasing, the tangent line will have a slope that's negative. And so the derivative will be negative. And if it's constant, which I had not drawn up here, so this is a constant function, and f of x sub 1 equals f of x sub 2, which is this y value right here, whatever that is. And the slope of the tangent line to that horizontal line will be equal to 0 at c. Okay. And by the way, that's a good use of the concept of trichotomy. I think I may have talked about it before, but if I haven't, this is not a bad idea. Whenever you're comparing two numbers, there are three possible things that are true. When comparing A and B, A is smaller than B, or A is equal to B, or A is greater than B. And a lot of times, oops, got ahead of myself. A lot of times what we're comparing to is the number 0. And so trichotomy usually covers all possible cases. That is, if something is compared to 0, it's either positive, 0, or negative. Those are the three possibilities. And so if we've talked about all three possibilities, there's not really anything else out there lurking in the shadows that we need to worry about. We've covered all bases if we've talked about positive, negative, and 0 values. Anyway, that's the idea of trichotomy. So if you look at figure 3.15, you've got a picture there of a function that's decreasing at first, and the first derivative is negative. Then from a to b, the function is constant, and that means its first derivative is 0. And when the function is increasing, the first derivative is positive. And so that's kind of just a picture to show you all three possibilities. So in Theorem 3.5, you'll notice below that the positive derivative tells us when the function is increasing. A negative derivative implies that the function is decreasing, and a 0 derivative on an entire interval implies that the function is constant on that interval. So the test for increasing and decreasing functions is Theorem 3.5, says that if the first derivative is positive on an interval, for all x in that interval, then f is increasing. Likewise, negative derivative gives us decreasing f. And if f prime is 0, then we have constant function on an interval. Okay, so let's use that definition, that test for increasing, decreasing, and find, they say, the open intervals on which f of x equals x cubed minus 3/2 x squared. Find the open intervals on which that function is increasing or decreasing. So since this is a polynomial function, we know that f is differentiable on the entire real number line, and that the derivative of f will be 3x squared minus 3/2 times the derivative of x squared, which is 2x, which simplifies to be 3x squared minus 3x. And then what we're going to do with that to find the critical numbers is say, when does that equal 0, or when does that fail to exist? So we're always going to start, when the question is about increasing or decreasing behavior, with the first derivative. We're going to find out when it's equal to 0 and when it doesn't exist. Well, since the derivative is a quadratic polynomial, it exists for every real number x. So the fact that it wouldn't exist never happens. So we can close off that line of inquiry. Over here where it's equal to 0, to solve that equation, we should probably notice that it factors. Common factor of 3x leaves x minus 1. And so that means 3x equals 0, or x minus 1 equals 0. So if 3x is 0, that means x is 0. But if x minus 1 is equal to 0, then x is equal to 1. Okay, now we're going to do something called a number line analysis. I think I may have said this before when we were talking about inequalities, but I'm going to pretend like I never said anything about it and teach you this from scratch. So draw a number line. It's called the number line analysis, and put all of your critical numbers on the number line from left to right, the correct values. So make sure that you've got them ordered on this number line correctly. Then label this f prime, because this is the first derivative number line analysis. And then that's a label above the line. And then below the line, label it f of x, because that's going to be the behavior that that first derivative value is indicating. Okay, so this is a well-labeled number line analysis. Now, one other thing. If you got the critical number from setting equal to 0, I want you to put a solid dot on the number line at those values. If we get anything from does not exist, which will happen pretty soon, you'll put an open circle around those so that you know where it came from. Now, that number line of all real numbers has been now separated into 3 separate regions. The things that are less than 0, the things between 0 and 1, and the things greater than 1. And the only way that you could have a sign change in your values, because it's a continuous function, is the only way it could go from positive to negative or negative to positive is if it went through 0 to change sign, or if it went over a place that you don't have a derivative existing. So that's why we label the number line with our critical numbers. So if I pick any number to the left of 0, like -3, and I calculate f prime at that number that I've chosen, that answer, I'm looking at whether it's positive or negative, will actually tell me what any number I could have picked to the left of 0 would also give me as far as its sign, positive or negative. So if I substitute -3 and I'm going to use this version of the first derivative right there. That's the one I like. So 3 times negative 3, actually I don't want to write equals. I'm going to use this version. But what I'm going to think of is what sign am I getting? So if I put negative 3 in, 3 times negative 3 is a negative number, times negative 3 minus 1, negative 4, is a negative number. Negative times negative is a positive result. And put a little plus sign above the number line saying that the first derivative is positive for any number you pick to the left of 0. So likewise, I'm going to do the same thing for the region from 0 to 1. I'm going to pick any number I like between 0 and 1, like 1/2. And I'm going to try to think about what its first derivative value would be. Again, using the check marked one, 3 times positive 1/2 is a positive number. 1/2 minus 1 is a negative number. Positive times negative is a negative number. Okay, now pick anything to the right of 1 to represent all numbers to the right of 1, like, I want 10. Again, it doesn't matter what number you pick over there. So 3 times 10 is positive. 10 minus 1 is positive. Positive times positive is positive. And all the stuff I wrote over here, you can do in your head if you want to. You need not show me that at all. In fact, I'd rather, if you're going to do it over to the side, and don't write it within the number line analysis, because I want that to be a pretty clean number line analysis without a lot of this kind of stuff I've written inside the box over here. I don't want that over here with the number line analysis, just the results, okay? Positive, negative, positive. Now, what we know from Theorem 3.5 is that if the first derivative is positive, that means that the function is increasing. And if the first derivative is negative, that means that the function is decreasing. And when the first derivative is positive, the function is increasing again. Okay? So we can now say, based on our number line analysis, that f is increasing on the intervals from negative infinity to 0. And it said open intervals, so they're wanting us to use an open 0 because they told us to. Then f is increasing on that interval, as well as, so union from 1 to infinity. F is decreasing on the interval from 0 to 1. So see how the number line analysis gives us all that information once we've completed it and done it correctly. Writing the answer is easy. You're just reading what the number line analysis tells you and recording it for me as an answer. So make sure you know how to do the number line analysis. It's really, really, really important. Okay. Now, in the book, you'll see they do a table instead. There's nothing wrong with that. I just think it's a lot of extra writing that I don't really want to do. So I really like for you to use the number line analysis. If you can do the table and do it absolutely correctly without any spots or blemishes or any little mess ups, then it's fine, because it is what the book tells you is going to work. But anyway, so if we were graphing this, in fact, you could pull out your calculator for this just to confirm our answers. And if you were to graph this, let's say this is 1. So make a few marks on the axis. Your graph should look like this. Oops, I messed up. Well, it's supposed to undo what I just did. There we go. Sorry about that, folks. That was disconcerting there for a second. Okay, so the function looks something like this. So obviously it's increasing until you get to 0. And then from 0 to 1, it's decreasing. And then from 1 to infinity, it's increasing. And so that's just a little visual confirmation that what we've decided is good. And you should come to rely on your answer using this number line analysis without having to check yourself on a graphing calculator. It's probably a good idea up front to kind of make sure that you are doing the right things and not making mistakes, that you check yourself on a graphing calculator, but please do try to work away from that so that you're not dependent on it. So if you look at the guidelines for finding intervals in which a function is increasing or decreasing, that's pretty much what we did, except for they're talking about using a table. And I would urge you to use the number line analysis instead because it's a whole lot less writing. Now, there's something called strictly monotonic. It's another vocabulary item for you to be aware of. A function is strictly monotonic if it is either non-decreasing on its domain, or non-increasing on its domain. Now, you may be thinking, well, why did he say that in that complicated way? Because if you're thinking about it, what does non-decreasing mean? Well, you may be thinking, well, that means it's increasing, and that's not necessarily so. If I say the term non-negative, oops, usually I can spell. Let me try again. Non-negative. Well, there's a distinction between that and positive numbers. They're not the same. The non-negative numbers are things that are either positive or 0, because 0 is not negative. Whereas if you said positive numbers, 0 is not included in there. So if I had said for the first statement, instead of non-decreasing, if I'd said increasing, it wouldn't have allowed for constant. So non-decreasing means it's either increasing or constant or a combination of the two. Okay? Non-increasing means it's either decreasing or constant or a combination of the two. So something that looks like this when you graph it is monotonic. Okay? Something that looks like this is monotonic. Something that looks like this is not monotonic because it has both increasing and decreasing behavior. Okay? So I just wanted you to see what this meant, this monotonic thing means. Now, in this section of the book, they actually use the word increasing instead of the word non-decreasing. And then later on in the book, when they're talking about monotonic things, they allow for what I've said. And so I'm using a definition that's actually going to be long-term better for you. And so what they're going to say is if it's constant, it's not monotonic. If it's got some interval where it's constant, they're going to say it's not monotonic. But then later they change their minds. So I'm going to kind of go with the long-term correct answer. I don't think it's going to matter to you much because it's very rare that you'll see a part of a function that's constant like figure 3.17. That doesn't happen very often in real situations. So let's just leave that alone for now. And if there is a question about whether something's monotonic or not, for right now, the correct answer will be if it's constant for an interval, then it's not monotonic, even though otherwise it may be increasing everywhere else. Later on, they'll say that that is monotonic, which is kind of irritating. But nevertheless, if you kind of keep that straight for now, I'm not going to ask anything like that on the test, so don't worry too much about it. If it's constant for a while, it's not going to be on the test, so don't worry about having to say that. But if it's strictly increasing or strictly decreasing, then it's definitely monotonic, like those two pictures I have there. All right. So now let's talk about the first derivative test. Once you've done the number line analysis, it's really not hard to find the relative extrema. Because if you'll remember, if there is a relative extremum, the first derivative has to be either 0 or non-existent. And so the critical numbers are candidates for where it might be a max or min. And what we're going to say is that anytime this happens, like what happens right here, that the first derivative changes from positive to negative at a value of x, like here at 0, that at 0, we're going to have a local or relative, I'm going to write local, max. That happens when the first derivative changes from positive to negative. Now, you could say, from a pre-calculus perspective, that the function is changing from increasing to decreasing. It's going up and then it's going down. Not that that's a false idea, but it's not a calculus idea. So if you're going to tell me that there's a local max and you're supposed to tell me why you know that's true, make sure you use calculus terminology. It's a local max at 0 here because the first derivative changes from positive to negative. So I'm going to write that down below. For that function, f has a local maximum that occurs at x equals 0. That's not saying what the maximum is, it's where it occurs. Okay, we'll get back to what it is in a second. At x equals 0 because f prime of x changes from positive to negative at x equals 0. And so if we were asked to find, well, what is the local maximum? The local maximum is the y value at the location of 0. And you would substitute that in to the function and you'd get 0. So the local maximum value is 0. And if you look at the graph, that should show you that this y value at this local maximum, that really is 0. Okay, so it's a little confirmation of the graph again. And remember, you're trying to do this without a graphing calculator, so you're trying to become independent of having to use the calculator. Okay, then you can tell that there's a local minimum here at 1, because a pre-calculus way of saying that is because you're changing from a decreasing to an increasing function. So it hits a low point right there. But the calculus explanation is you'll have a local minimum when the first derivative changes from negative to positive. Okay, so let me say that down below as well. F has a local minimum at x equals 1 because f prime changes from negative to positive at x equals 1. Okay, so that tells us we have a local minimum at x equals 1. And if you wanted to know the value of that local minimum, you'd have to substitute 1 into the function. And you should get negative 1/2, which is the y-coordinate of that local minimum that I plotted up above, right there. Okay, so that's how we'll find the extrema. This is called the first derivative test, where the sign change at a critical number of where there's actually a point on the curve, and there's a critical number, and a sign change in the first derivative indicates a local extremum. If it's from positive to negative as you're moving from left to right, it'll be a local maximum. If it's a change from negative to positive, there'll be a local minimum. Okay, so that's basically the first derivative test. They may ask this, and I don't really like it, but they will do this. At times, if they ask you to find the maximum, they may ask you to write that as an ordered pair. The maximum is really just the y value, but they may prompt you for an ordered pair. So please be aware that the actual maximum is just the y value, but they may record it so that they can know that you knew the x and the y where that occurred. So they'll have you write it as an ordered pair, but keep in mind, this is what I'll be asking for, is the y value. If I say what's the local maximum or what's the local minimum, I'm looking for the y value, not the point. All right. So if you look at Theorem 3.6, that's the first derivative test. If c is a critical number of a function that's continuous on an open interval I that contains c, if f is differentiable on the interval except possibly at c, then f of c can be classified as follows. If f prime changes from negative to positive at c, then f has a relative minimum. There. If f prime changes from positive to negative at c, then there'll be a relative maximum there. If f prime is positive on both sides or negative on both sides of c, then f of c is neither a relative minimum nor a relative maximum. So those last two pictures at the bottom of Theorem 3.6 show first derivative positive, critical number at c, first derivative positive, so it's increasing, horizontal tangent line increasing. That's that saddle point I mentioned earlier. So just remember, if you get a critical number, that doesn't mean you necessarily do have a max or min there. It's just potentially. And in fact, it only happens with a sign change at x equals c, from positive to negative for local max or from negative to positive for local min. But if the sign doesn't change, then there's no local max nor local min at x equals c. Okay, so let's look at another example. Look at example 2, and I'm going to give you a minute to look at that on your own, see what you can do. All right, so let's see how you did. It says find the relative extrema of f of x equals 1/2 x minus sine of x in the interval from 0 to 2 pi. Okay, so first of all, 1/2 x is a polynomial function, and it's continuous for all reals. And sine of x is a trigonometric function that's continuous on its domain, which is all real numbers. And so the difference of two continuous functions for all reals will be continuous for all reals. And therefore, f of x is continuous for sure on the subinterval of all reals from 0 to 2 pi. So we have continuity. That means we can continue. So to find the relative extrema for that continuous function, we're going to find the first derivative. So the derivative of 1/2 x is 1/2 minus the derivative of sine of x is cosine of x. And you're going to hear me say this over and over again, so might as well just get used to this idea. Take that first derivative, first set it equal to 0, then write the word or, and then write f prime of x, d and e. And I usually start with that because if that isn't an issue, I can dismiss it early and I won't have to think about it again. Is there any number x that could not be put into our first derivative? No, we can take the cosine of any real number. So that will never happen that the first derivative will fail to exist. There's no division by 0 possible, for example. So we're going to forget that doesn't exist. I promise we'll see that at some point, but just not yet. So if I solve for cosine of x will equal 1/2. And cosine of x is equal to 1/2 on the interval from 0 to 2 pi. That happens at pi over 3. And again at 5 pi over 3. And again, if you're not able to get those relatively quickly, those two values, you need to go back and look at your pre-cal again and make sure that you know how to get those values. Okay, so those are our critical numbers on our interval. So do the number line analysis. Put pi over 3. We got that from equals 0, so put a solid dot. Put 5 pi over 3 to its right. And we got it from equals 0, so solid dot. This is called the first derivative number line analysis. And it will give us information about the behavior of our function f. And because we have a restricted domain, I'm going to put 0 and 2 pi as things which we're not going to cross past at all. Okay, so looking at our first derivative, between 0 and pi over 3, I'm going to pick pi over 6. Why not? So at pi over 6, 1/2 is positive, so it's positive 1/2, minus cosine of pi over 6. The cosine of pi over 6 is square root of 3 over 2. And square root of 3 is somewhere between square root of 1, which is 1, and square root of 4, which is 2. So it's got a numerator bigger than 1. 1/2 minus more than 1/2, like 1.5 if that's what it is. It's not, but let's pretend. Then that's going to give us a negative answer. And so this is negative. Then from pi over 3 to 5 pi over 3, I'm going to pick something that's easy, like pi. You can pick anything you want, and I'm going to pick pi because it's easy. So 1/2 minus cosine of pi is negative 1. 1/2 minus negative 1 is positive. So I'll put a plus here. And then from 5 pi over 3 to 2 pi, I guess 11 pi over 6 is fine. Um, 1/2 minus cosine of 11 pi over 6 is square root of 3 over 2, which will give us a negative answer. So that's negative. All right. So that means that the function is decreasing, increasing, decreasing. Now, be careful that you read the directions, because there are lots of things you could be asked for here. You could be asked, like in the prior example, for intervals where the function increases or decreases. And you could address that. But this one just asks us for the relative extrema. So I'm not going to write where it's increasing, decreasing, other than what shows up in my number line analysis. But I could turn that into a sentence or two to describe those intervals if I were asked. It's not what the question was, so let's not dwell on that. Okay, so the function is, the first derivative changes from negative to positive at pi over 3. So that means that we know we have a local minimum there. So let's say that there's a local minimum at x equals pi over 3. And we know that's true. Why? Because, make sure you make a calculus argument, not a pre-calculus argument, because f prime changes from negative to positive at x equals pi over 3. Okay. And it said to find the relative extrema, which means we're going to need to find the local minimum, which is the value of it, not its location. So the local minimum is f of pi over 3. So please make sure you substitute back into the original function, not the derivative function for this. So this is 1/2 times pi over 3 minus the sine of pi over 3 which is pi over 6 minus the square root of 3 over 2. And if let's see, yeah, we can leave it like that. I was going to say, if you get a common denominator, that would be pi minus 3 square roots of 3 all over 6 is also a good valid answer. Okay, then because f prime changes from positive to negative at 5 pi over 3, that means that we have a local maximum there. So say all of that in words. There's a local maximum. At x equals 5 pi over 3. Because f prime changes from positive to negative at x equals 5 pi over 3. And the question was for the extrema, so the local maximum extreme value is f of 5 pi over 3 which is 1/2 times 5 pi over 3 minus sine of 5 pi over 3, which is 5 pi over 6 minus negative square root of 3 over 2, or in other words, 5 pi plus 3 square roots of 3 all over 6. Okay. So we have that. Good. That is the end of that section. So I will close this off and say I'll see you in class.